the physics behind flute acoustics. Our objectives of this project was to explain the physics of how flute works and how notes and octaves in music are achieved.
First, what we'll cover is the resonance and sounding frequencies of the flute. Next, we'll briefly touch on differences in materials based on previous research. Finally, we'll delve into the physics complexities of the flute, involving wavelength, frequency, and harmonic numbers.
Our first source was an article called Resonance and Sounding Frequencies of the Flute. This article examined the important effects of temperature, air condition, lip coverage, and blowing pressure in regards to octaves and frequencies. On the flute, only 3 octaves are able to be played due to restrictions of the structure.
On the flute, frequencies are obtained by blowing across the mouthpiece and covering certain finger keys, which are holes on the instrument which vary the length of the tube. Natural frequencies are based on the length of the tube. A major part of frequency determination is lip coverage of the hole on the mouthpiece, as this affects the octave and pitch produced.
As highlighted by this figure, lower octave notes are heard when there's less coverage of the embouchure hole on the mouthpiece. As the coverage increases, the notes get progressively higher. Hence, there's an inverse relationship as illustrated in this graph.
In order to create a desired note with minimal effort, lip configuration and pushing the lips forward to cover the mouthpiece is utilized to achieve a higher octave by raising the stream velocity. Blowing pressure is a key factor as well. As illustrated above, as the blowing pressures increase, the octave also increases.
Finally, temperature and air content is another important factor to consider. The speed of sound is affected by a flutist's breath due to temperature, humidity, and carbon dioxide content. Water droplets in the breath increase the velocity of sound. Temperature also affects the speed of sound. This is why flutes must be warmed up before performing, otherwise the notes will be effective.
Our second objective mentioned was the quality of the material. There is no evidence based on experiments containing trained and untrained musicians that a difference is heard between 3 different materials, which were copper, silver, and wood. It was noted, however, that one player pointed out that one of the 3 instruments was flat, which was the copper-made flute. This makes sense, as copper takes longer to warm up due to its high thermal mass. This can account for why in flute construction, some materials are preferred over others.
Lastly, as explained in the OpenStax textbook, a flute is an example of a resonance in a tube that's open on both ends. It has an antinote on each end, allowing air molecules to move freely. As mentioned before, the pitch of the flute is altered by varying the length of the tube by opening and closing finger holes. The shorter the tube, the higher the octave in the note is. In addition, it is important to note that the fundamental frequency, which has a wavelength twice as long as a flute, corresponds to the lowest note on the flute.
Regarding the math behind the physics concepts is this table. N corresponds to the number of nodes present in the tube. As seen by the equation, the fundamental frequency is n equals 1, and for open tubes, n equals 1 and any integer to infinity. As seen by the wavelength equation, if L is kept constant, the larger n is, the smaller the wavelength. The frequency is affected by the equation shown in this point, which is frequency equals n times the velocity over 2L, which is a variation of the frequency equation in the chart. As n increases, frequency increases as well.
Sofia will now demonstrate the different octaves of the note D.
On the flute, the lowest note D involves holding all the finger holes down, which sounds like this. And this is the longest length of the flute. Next, when you go to middle D, which is an octave higher, you lift up one note, which alters the length of the tube, and you can blow differently. Finally, the highest octave of D able to be played on the flute is high D, and to play that, you lift up all these fingers, and you can use blowing techniques and lip coverage to alter it.
To conclude, the physics behind the flute is based on lip coverage, temperature, pressure, and the length of the tube, which affects wavelengths and frequencies. Thank you.